Thank you, Charki, and hello, everyone. So let me start by thanking the organizers for continuing this very good effort. So today I'll be talking about some of the recent works that we have been doing. This work has been done with Etienne Hubris and Roderick Moisner. So I'll be talking about the effect of external electric field on a quantum spinized material, which is basically an example of a quantum spin liquid in 3 dimensions. So let me give some background. So what we are looking at are charge responses in magnetic insulators. In particular, let's think about electrons on a lattice and consider half filling, which is 1 electron per site. The good paradigm to think about these kind of systems is starting with Hubbard type of models, which has kinetic energy part denoting the hopping of electrons and on-site Coulomb repulsion. So that's the potential energy part. When the kinetic energy part wins out, we have a metallic system. The ground state is a metal. And when the potential energy wins out, the electrons localize and we have an insulator. And we basically have spin half magnetic moments at every site. So, so at low energies, much below the charge gap, the effective energetics is controlled by virtual charge fluctuations, which lead to spin Hamiltonians of this type. Related to the parameters of the spin Hamiltonian can be related to the parameters of the Hubbard Hamiltonian in this way. And this is generated by, as we know, from virtual hopping of electron going from one side to another and coming back. This is a typical second order process which contributes to this Hamiltonian. So one of the things is that because of virtual charge fluctuation, not only the energetics becomes non-trivial at low energy, but also there is the development of electric polarization. So in the underlying Hubbard model, there is a on-site charge operator, which is a bilinear of the fermion operators. But because at finite hopping, there is virtual charge fluctuation, there is an effective charge operator at low energies, which at u equal to infinity is 1, which is like 1 electron per site. But at finite t, it gets renormalized. For example, on a triangle, if I think about the effective charge on site 1, it gets renormalized in this way, and this renormalization depends upon the spins, just like I generate the Heisenberg spin Hamiltonian, and this was pointed out by these people. So, the interesting thing is that such charge fluctuation can lead to the development of electric polarization in magnetic insulators, and there are also contributions from lattice distortions and phonon when we consider the motion of the lattice. So what we will discuss in this talk is what do this electric polarization do. It turns out that basically from the symmetry considerations, the form of this electric polarization moment is essentially fixed up to coupling constants. So roughly anything that transforms as a 3-component vector in 3 dimensions under lattice symmetries and is even under time reversal and odd under inversion is proportional to a electric polarization operator. And when I put an electric field, it can give rise to magnetoelectric effect. And this is essentially what happens in multiferroics, where the inversion symmetry is explicitly broken or spontaneously broken. So, but what we want to do is to go beyond multiferroics, where there is no spontaneous or explicit breaking of inversion symmetry. So essentially, I'll discuss the properties of this kind of perturbations in spin systems where there is no inversion symmetry being broken, and ask what is the effect of this type of perturbations when I put the system in an external electric field DC. So if it turns out that this kind of systems, most of them order magnetically at low temperature, and even though these type of magnetoelectric effects can be interesting in these systems, they are in a way secondary, because there are other prominent effects which like neutron scattering, etc., which completely characterizes the low energy properties. And so it's not very interesting to look at these effects. But what the question that we want to ask is, what happens if the system doesn't order to the lowest temperatures and we get what are known as quantum spin liquids? In particular, I'll try to ask what happens to this particular quantum spin liquid, which is called a quantum spin ice, which is a 3D Yuan spin liquid on a pyrochlore lattice. So this is a pyrochlore lattice, and the Hamiltonian, the minimal Hamiltonian is given by this. It's an XXZ Hamiltonian. These type of systems, the candidate materials being rare earth pyrochlores, do not have spin rotation symmetry, and usually this Ising coupling is much bigger than this transverse coupling. So, if I, the right point to start is to first neglect the quantum coupling and try to understand what this Ising coupling does. And because of this corner sharing geometry, you can write it in this way, that sum of the total spin coming from each tetrahedron square, and then sum over the tetrahedra. And this immediately means that I need to minimize the total spin per tetrahedra, and that can be obtained by putting two spins up and two spins down, or in this fashion, because the Ising axes differ from side to side, two in and two out. And this is the famous two in, two out Ice rule, because of its similarity with regular ice, as was studied by Pauling way back. And we know that there are macroscopic number of ways to do this, and this leads to zero temperature entropy in the classical system by about log 0.5, half of log 0.5 per side. Okay, so what happens when we put in quantum effects? Of course, we need to quench this zero temperature entropy, and this can be done in two ways. One is the more conventional way. These quantum fluctuations actually lead to ordering, which is known as quantum order by disorder. And when it orders, I basically get rid of the macroscopic entropy. But the other interesting way that it can get rid of this macroscopic entropy is by developing long-range entanglement, and this leads to topologically ordered phases, quantum spin liquid being the example. Okay, so in particular, this particular system seems to take the second rule, which is route, which is why it is interesting. And to give you a brief idea of how this happens, the Ice rules this zero net moment per tetrahedron. If you draw a sphere around this single tetrahedron, it roughly translates into zero flux of these field out of this sphere, and which can be written in terms of a Gauss's law type of constraint, and this B being an emergent magnetic field. Okay, so if I add quantum dynamics to this, so if I single spin flip these flip spin, so a single spin flip is not allowed, because then I create violate these two in two out rules in these two. Suppose I flip this spin, I violate the constraint in these two tetrahedra, and these single spin flip violating the Gauss's law can lead to magnetic monopole type of excitation, as studied by these people. So the lowest ordered spin flip in this low energy manifold is actually when you flip spins along the around this loop of 6 spins, and this gives rise to this kind of hopping process at the third order. And when you write it down in a similar electromagnetic way, it leads to dynamics or the emergent electric field term. Okay. So when we gather everything, we basically get a lattice effective theory, which looks very much like our electromagnetism, but a compact Yuan gauge theory in 3D. And this has two phases: the confined phase, or the area phase, which is actually some ordered phase, and the deconfined phase, or the perimeter phase of the gauge theory, which is our Yuan quantum spin liquid. Okay, so we will focus on this deconfined phase, and in this compact Yuan gauge theory in 3D, in this deconfined phase has low energy gapless excitation, which is a gapless gauge boson or an emergent photon, and this gauge invariance is emergent at low energy. Okay, so what we want to ask is that what happens in this phase for this system when I put in an external electric field, and there is a the electric moment. polarization moment. So as I said that you can calculate the form of this electric polarization operator using the symmetries. In this case, the symmetry of the pyrochlore lattice, and this is the expression. I won't try to discuss this, but let me point out there is a longitudinal part which only depends upon the Ising part or the SZ part of the spins, and then there is this transverse part which depends upon the spin flip terms, the X and Y. So this is a sort of the quantum contribution to this. Okay, so what we want to do is to calculate the effect of these things in this limit. And if I redo my calculations of the low energy effective Hamiltonian, I get these extra terms, chi being this ratio of these electric field strengths to the underlying quantum term. And I want to ask what happens as I change my external electric field. So it turns out that below a critical value of chi for low electric field, I can expand this cosine out, and this basically gives rise to more Maxwell-like Hamiltonian, and I can with the direction of this coupling being dependent on the direction of the external field. And so what happens is that this underlying emergent photon dispersion becomes, it starts showing birefringence in the sense that the velocity of this, the photon starts depending upon the direction and the polarization of this emergent light. And this has a direct consequence to the underlying spin structure factor from the underlying spins. As you can see that I can, when I increase this one certain particular plane, as I increase the electric field, the structure factor changes. And that's something that experimentally is observable. Close to this critical chi, I developed sharp structures in the spin structure factor, equal time spin structure factor, which are variously known as pinch points. So that's also a detecting feature. And finally, once I increase chi below above this critical value, as you can see that this terms this coupling constants change sign, and then almost done. So this coupling constant change sign, and I have to basically expand the cosine about a pi flux, and this drives a phase transition between U1 quantum spin liquids with and without electric flux, and this is an interesting example of phase transition between long range entangled states without ordering. So is this effect observable? So in candidate rare earth pyrochlores, it turns out that this longitudinal coupling is about 1 Kelvin, whereas the transverse coupling is about 100 millikelvin. So if you put in the numbers and try to make an estimate of the external electric field that we require to make this effect sizable, it's about 10 to the power 4 volts per millimeter, which is what is experimentally very much accessible. So that's where I would end. Thank you.
You said it's kind of observable, so electromagnetic field will couple to this mode, or?
Yes. So that's right now. So what I have explained is coupling of the DC field, but AC field would also have more interesting effects like converting a real photon to this emergent photon. So that's. So it turns out that for collinear ordering, this fluctuation is suppressed, but for non-collinear ordering, say on a triangular lattice spiral magnet, this the effect can be very pronounced. But as I said, that there are other effects there which already characterizes the state, like it.